Hello and welcome to the live broadcast of the Lightning God Defends mission, our 93rd Electron launch and the latest for Japan's Institute of Kyushu Pioneers of Space, known as iQPS. Liftoff is just 18 minutes away at Rocket Lab Launch Complex 1 on the Mahia Peninsula, with launch set for 0104 a.m. local time. I'm Muriel Baker, and we are joining you from our Mission Control Centre in Auckland, some 600 kilometres northwest of Mahia.
And I'm Likita Satursala, and we're thrilled to be on the pad once again for iQPS. Today's mission will be our 14th launch of 2026 and the latest for iQPS as they continue to build out their constellation of synthetic aperture radar satellites, designed to deliver near real-time Earth observation in any weather, day or night. The skies are calm and clear over the launch pad this morning, with just a 20% chance of exceeding weather constraints. We've had good comms throughout the count so far, and the team is reporting no issues.
Now today we are targeting a 575-kilometre low Earth orbit at a 42-degree inclination from Launch Complex 1. An onboard Electron is the QPS-SAR satellite for iQPS, nicknamed SUSANOO for the Japanese god of storms. Now, as with all iQPS missions so far, the launch name pays homage to a Japanese deity that is selected to represent the role of that next satellite in their Earth imaging constellation. We've launched missions named after gods and goddesses of wisdom, the ocean, and the mountains. But today's mission is the first time that we're flying the Lightning God for the second time for this constellation.
Now, if you're not familiar with SAR, get your notebooks out because here's how it works. It uses radio waves to bounce off terrain and objects below, capturing high-resolution images regardless of weather or time of day. Normal observation satellites use optical lenses, but if there's clouds in the way, or it's nighttime, those optical sensors are no good. This is what makes synthetic aperture radar so special. iQPS can image almost anywhere on Earth in near real time, providing critical insights for things like emergency response, shipping routes, land management, and more. So here's more from iQPS.
Founded in Fukuoka with the mission of establishing a space industry in Kyushu, iQPS marks its 20th anniversary in 2025. Today, together with more than 25 partner companies, mainly based in northern Kyushu, we are developing the world-class small SAR satellite, QPS-SAR. SAR satellites use radio waves, enabling observation of the Earth's surface day or night in any weather. iQPS is steadily working toward a 36-satellite QPS-SAR constellation, aiming for near real-time Earth observation almost anywhere on the globe. Since launching our first satellite in December 2019, we have continued to expand our fleet and gained extensive expertise in operations. In March 2025, our new R&D hub, QSIP, was established. QSIP integrates manufacturing, testing, and shipping on one floor, enabling production of up to 10 satellites per year. This boosts efficiency and development speed, accelerating launches and service readiness. Partnering with government agencies, infrastructure operators, and others, we are already delivering results by combining satellite data with image analysis and AI. Our satellites are used for inspecting large infrastructure and monitoring wildfires, earthquakes, eruptions, and other disasters, helping detect crises early. As natural disasters and geopolitical risks increase worldwide, the need for our high-precision observation data grows more urgent every day. Faster, more accurate, covering more places than ever before. We will continue expanding our constellation, realizing a world where Earth is observed more frequently. unlocking the potential of space and contributing to human progress. The challenge of iQPS continues.
Now, so far, we've successfully launched 8 missions for iQPS, all taking place at Launch Complex 1 with plenty more on the way.
That's right. In fact, just last month we announced a new deal with iQPS for 3 more launches, the third multi-launch booking on Electron they've made in less than a year. But still, today's focus is on the QPS-SAR satellite that we're preparing to send to low Earth orbit today in just 12 minutes' time.
Prior to liftoff, our launch operations team must conduct the launch status check, also known as the go-no-go poll. This is a vital part of the launch process to ensure all systems are working properly before Electron's flight computer takes over the countdown itself. The poll kicks off at exactly T-minus 12 minutes, and once it's complete, Electron's flight computer will take over the countdown. Let's hand it over to Launch Director Julia Wimbacher to run through the status of key systems.
And to all operators, LD and mission code, we're proceeding now with the go-no-go sequence, starting with stage.
Stage is go.
Avionics.
Avionics is go.
GNC.
GNC is go.
VCON.
VCON is go.
T1.
T1 is go.
GC.
GC is go.
PLS.
PLS is go.
RSO.
RSO is go.
MET.
MET is go.
MM.
MM is go.
FAN.
FAN is go.
LSO.
LSO is go.
LD sub.
LD sub is go.
The go-no-go sequence is complete. We are T-minus 11 minutes and 16 seconds and counting. We go for the terminal count auto sequence at T-minus 10 minutes. From this time, the 3-web procedure is in effect.
Okay, all systems are go from our operators in mission control and range control, and that confirmation clears the way for the final milestones ahead of liftoff. T0 is on scheduled for 1:04 local time, which is 13:04 UTC or 10:04 PM for our iQPS partners in Japan.
Right on time, just how we like it. Okay, so today marks Electron's 14th launch of 2026 and another step closer to a 100th launch milestone in the coming weeks. The Electron you see on your screen is in its standard configuration, a 2-stage launch vehicle with a third in-space maneuvering platform called the kick stage. At about 18 meters tall, or close to 60 feet, Electron can deliver small satellites of up to 320 kilograms into precise orbits, and can even deliver payloads to the moon. Even more, Electron's kick stage takes customers directly to their desired orbit, exactly when they need to get there. No ride-sharing required. Another key difference is Electron's revolutionary propulsion system. At the base of the first stage are 9 Rutherford engines, and stage 2 is powered by a single Rutherford engine modified for the vacuum conditions of space. These engines are the first in the world to use an electric pump-fed cycle powered by lithium polymer batteries, which eliminates the need for complex turbomachinery. Those Rutherford engines are almost entirely 3D printed, with the main components manufactured in just 24 hours, enabling rapid production and scalability.
It's those 3D printed engines that ignite at T-minus 2 seconds just before the launch mount's hold-down mechanisms are released and Electron begins its journey to space. Now, after engine ignition, it'll take about 9 minutes to deliver the kick stage to its nominal transfer orbit. So here's how it all happens. The first stage's job is to get us out of Earth's atmosphere. It's basically a giant fuel tank with 9 engines at the bottom, and it will burn for about 2.5 minutes before shutting down to allow the second stage to separate and ignite its vacuum-optimized Rutherford engine. Over the next 6.5 minutes, we'll hit key milestones like fairing jettison, and battery hot swap. And then after that, the second stage will separate, sending the kick stage and iQPS's satellite on their way. And then from there, the kick stage will enter a quiet 40-minute coast phase around the Earth. And then once it reaches the right position, the kick stage will fire its Curie engine to circularize the orbit and deploy the satellite at its target altitude of 575 kilometers.
Now, this morning's launch will be our 11th flight from LC-1 this year, with the other 3 missions in 2026 lifting off from LC-2. Then, of course, there will be the debut of Neutron from right next door in Virginia from Launch Complex 3. Well, in some more recent exciting news, we're officially adding a Launch Complex 4 to the list in Kodiak, Alaska, for our new deployable launch system called GHOST.
Now, the acronym stands for Global Hypersonic and Orbital Spaceport Technology, and in your standard-sized shipping containers, we'll be able to deliver Electron and HASTE to wherever they're needed. And that includes spaceport tech that we've made deployable, like our rocket's launch infrastructure, ground support, and range control systems. Here's more about GHOST.
Rocket Lab has mastered the art of building launch sites. Now, we're making them deployable with GHOST, turning our Electron and HASTE rockets into a launch anywhere, launch anytime capability that meets the most demanding missions.
Strengthening America's missile defense capability is incredibly important. Analysis only gets you so far. Eventually, you need to be producing hardware and testing it in the field. If you cannot test your missile defense system at a high cadence, frankly, you're just not going to keep pace with the threat because you're not evolving your own capability as quickly as you could. Missile defense testing is often more geographically relevant, and so there need to be missile defense tests in the Atlantic. They need to be in the Pacific. They need to be at partner nations. And so that's why developing the capability to perform those tests in those areas is so important.
Pack it, ship it, launch it. GHOST can deploy rockets, infrastructure, ground support equipment, and range control systems from standard shipping containers to anywhere in the world.
Speed on station, speed to orbit, speed to test. Speed has been the name of the game in recent national security applications. And so our ability to deploy this quickly, get into a launch campaign, pick it up and move it, not only does it make it very affordable because you're not spending a lot of time waiting around, but it is exactly what the government has been looking for in terms of moving at the pace of the threat, accomplishing a lot of tests in a given year, and not having to spend a whole bunch of money to do so. Kodiak, Alaska was the right solution for the first deployment of our mobile launch architecture, really in support of our missile defense customers who needed Pacific access. But it's important to remember that HASTE and Electron use the same launch infrastructure. And so not only is this a suborbital capability, but this is now an orbital launch capability that we can bring anywhere in the world.
More orbital options, hypersonic flight tests on demand, accelerated timelines. GHOST is purpose-built for rapid activation within days and multiple missions at once, bringing launch to the location that serves the mission.
Rocket Lab's approach to deployable launch infrastructure sets us apart from basically everybody else because it's Electron, and we've demonstrated a high-rate, reliable launch capability. That's really the discriminator. And so our approach is to bring that level of reliability into a mobile architecture that can be moved around. Now, once you complete a launch campaign, you're able to package that up and move it somewhere else. That somewhere else can be addressing a missile defense application, something suborbital or orbital. And if you can move a launch site somewhere near the equator, if you can move it to a partner nation, now you can address sovereign launch capability and you can address a variety of new orbits, which open up new markets. Execution is key. We have the credibility to execute, and now we're bringing that into a new application. It's a very exciting time to say that now we have the capability, we have the hardware and the infrastructure to move this around and go address new global markets.
Well, I'm definitely putting my hand up to host a webcast from Alaska for our first launch from GHOST next year, because if you didn't already know, GHOST is going to anchor our largest launch contract ever for up to 18 suborbital launches for the Space Force's Space Systems Command. And like Brian was saying in that clip, who knows where GHOST could go next, since both Electron and HASTE share the same infrastructure. So it's entirely possible that GHOST could support missile defense or sovereign launch in other locations around the world.
All right, let's turn our attention back to today's mission for iQPS. The Lightning God is just 3 minutes and 53 seconds away from liftoff, and Electron is getting ready to transition to its internal power. Its onboard flight computer will take over the countdown from here, so you'll hear the launch director confirm these milestones over the loops from mission control as they happen. Next, the propellant loading will wrap up, followed by tank pressure optimization to ensure Electron's tanks are fully pressed for flight. The launch director will monitor for any critical flags during this final count. So if it all goes well, they'll call out the countdown from T-minus 10 seconds, leading us straight to liftoff at T0. So now let's listen to mission control for these final moments.
To all operators, LDN mission code. From now on, there should be no red flags on your critical LCCs. VCON LDN mission code.
LD VCON.
Please lock the auto sequence and confirm.
Confirmed.
And please confirm all flight computer ASCOs are green.
All ASCOs are green.
To all operators, we go for auto sequence start at T-minus 2 minutes. LDs go for launch.
UCS disabled.
The vehicle is fully on internal power. AFTS is green and enabled for flight.
Lock load is complete. System is in recirculation. Anti-gathering is disabled. Stage 1 and Stage 2 tanks are pressed.
High flow engine purge enabled.
T-minus 20 seconds and counting. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1.
Beginning control. Stage 1 propulsion nominal.
Electron is on its way to orbit for the Lightning God Defend, now more than 3 kilometers above Earth and traveling at speeds of over 700 kilometers per hour, which means we are fast approaching our first major milestone called max Q, or maximum aerodynamic pressure. Now, max Q is important because it's the point of the greatest structural stress, and so we should hear that moment and confirmation from Mission Control shortly.
Cleared max Q.
And there it is, max Q cleared. Electron is now traveling at more than 2,000 kilometers an hour and climbing steadily. Next, we're entering a dynamic phase of the flight with 3 rapid milestones: main engine cutoff, or MECO, state separation, and second stage engine ignition. First, the 9 Rutherford engines on the first stage will slow down and shut off completely, and within seconds, the first stage will separate, and the second stage's Rutherford engine will ignite to continue the journey to orbit. Listen closely for the sound of the Rutherford engine's fuel pumps winding up for ignition. This is scheduled to happen around T plus 2 minutes and 30 seconds into flight.
Roughly 30 seconds. "15 seconds to staging.
Entered burnout detect mode.
MECO confirmed.
Stage separation confirmed.
Stage 2 ignition confirmed.
And there we have it, confirmation of MECO, stage separation and a successful ignition of that second stage engine. It's firing as we expect and propelling our mission closer to orbit at a speed of over 8,000 kilometers per hour. Now you can see the satellite housed inside Electron's fairing on your right there. It's sitting atop the kick stage. The fairing that's over the top of it is protecting the satellite from the intense friction of the upper atmosphere, but it won't be needed for much longer. So soon it will separate and fall away, and we're standing by now for confirmation of that from Mission Control.
HEB discharge holding nominal.
Fairing jettison confirmed.
Stage 2 propulsion nominal.
Oh, it might have had a camera issue there, but we have had confirmation that the fairing has successfully jettisoned. And right now we are at more than 4 minutes into flight with under 6 minutes left in this second stage burn.
Stage 2 propulsion holding nominal.
Coming up next, you'll hear a couple of key call-outs from Mission Control related to the Rutherford engine's battery-powered, electrically driven pumps. Now, the second stage burn lasts about 3 times longer than the first stage, which means we need more battery power to keep the engine running. But like any battery, they eventually drain and need to be replaced, and that's where the battery hot swap comes in. This maneuver is a critical step in the second stage's journey to orbit. It involves switching from the depleted batteries to a fresh set without missing a beat. You can actually see the silver rectangular battery packs on your screen right now. During the hot swap, the pack in the bottom right corner will disconnect and fall away from the vehicle. That will be our visual confirmation that the hot swap was successful. So let's listen in now for the call out from Mission Control.
HEB discharge holding nominal. Approaching hot swap in roughly 30 seconds.
Charging down.
Battery jettison confirmed.
Confirm hot swap successful.
Excellent. Battery hot swap confirmed, and the second stage engine is performing nominally, and we're checking off these final milestones of this phase of this mission. But next up, we'll be looking for SECO, second engine cutoff, and the separation of the kick stage. And this process is similar to what we saw earlier with the first and second stages, but instead of the main engine shutting down, it will be that second stage engine.
Once the kick stage separates, it will carry the iQPS satellite into its transfer orbit. This elliptical orbit is designed to bring the kick stage to the altitude of its final circular orbit at 575 kilometers above Earth. That journey will take about 40 minutes. When the kick stage reaches its target, its Curie engine will ignite to perform the final maneuver needed to circularize the orbit.
But before we get there, we still need to complete SECO and the separation of the kick stage from that second stage. And that is coming up in just a few moments. So let's listen in for those call-outs. We've just passed 8 minutes into flight now, coming up on stage 2, separation, and we can see that we're performing nominally on our way to orbit with a speed of more than 22,000 kilometers per hour, now above 263 kilometers above Earth.
Guidance is in terminal. 20 seconds remaining. SECO confirmed.
Stage separation confirmed.
Nominal transfer orbit achieved.
And there it is, second engine cutoff confirmed, and the kick stage has successfully separated from the second stage. It's now in its planned transfer orbit, a huge milestone for team and the mission so far.
Yes, not a bad way to travel 1,500 kilometers downrange in such a short amount of time. But now, as we mentioned earlier, the kick stage is in its 40-minute coast phase around the Earth. And once it reaches the other side of the planet, its Curie engine will ignite to perform a final burn that places the satellite into its target circular orbit. Then after that, we'll be just moments away from deploying the QPS-SAR satellite to add another key asset to their Earth imaging constellation.
We'll rejoin you shortly to listen in on those final moments before payload deployment. In the meantime, you can follow the kick stage's progress on the tracking graphic on your screen shortly as it continues its journey around Earth. We'll see you back here soon.
T plus 48 minutes or so, and we are back, and you are joining us just in time for the final moments of this mission, our dedicated Electron launch for Japan-based iQPS. Now, if you missed the earlier action, here is a quick recap. We had a smooth liftoff and made our way through max Q, main engine cutoff, stage separation, and second stage ignition. The second stage has delivered the kick stage and its payload into a nominal transfer orbit, and we have since completed the elliptical phase of this journey.
And now the kick stage is in its target circular low Earth orbit, and we're just moments away from deploying the satellite into the iQPS constellation. We're standing by for confirmation of Curie engine shutdown, which will signal that we're just seconds away from payload deployment. So let's listen in.
Curie cutoff confirmed. Nominal final orbit achieved.
Shutdown confirmed. So now we are just moments to go until we deploy the latest spacecraft to the iQPS constellation.
Payload deployment confirmed. Another successful mission for Electron and iQPS. This launch adds another satellite to the growing QPS-SAR constellation in low Earth orbit. Congratulations to the entire mission team and to iQPS as they begin the commissioning process for the newest satellite. That wraps up Electron's 93rd launch and 14th of this year. We're just a few launches away from hitting the big 100, and we can't wait to celebrate that milestone with you soon.
Now, before we close out, a reminder that if you like what you saw today and you want to join the team redefining access to space, then visit rocketlabcareers.com and make sure to follow us on social media to stay in our orbit. Otherwise, thank you for joining us today. This is Rocket Lab Mission Control signing off.